get you to log. Okay, yes.
Now, where is this?
It's going to be at the EMO building. Hello there.
Okay.
It's going to be at the EMO building. You know where the old MTO building was? Okay, you know where Water Tower Inn is?
Yeah.
Okay, on the street behind the Water Tower Inn, go opposite, and it's the MTO building. Old Garden River Road.
Okay.
It's on Old Garden. It's a big building. It's got a big radio antenna up there.
Okay, is that the one that's on the left side or on the right side?
Well, it depends if you're going up or down.
Yeah.
If you're going down, it would be on your
Same side
right.
as the Sioux Star.
Same side as the Sioux Star. Up from the Sioux Star. It's a big building. It's actually a fire hall.
Okay.
Yeah. So
That's where the event.
that's where we're going to have a contest. It's a single sideband contest. Okay. Starts at 8 o'clock, I believe, on the 28th, Friday the 28th. Starts. I'll send you all of this stuff. Okay. And you're just doing what amateurs do. You'll be calling CQ and answering the guy, getting his call, and giving him, I don't know what, you'll give him some information, you get some information, you enter it on the computer, and you just move on to the next one. We do this for 48 hours.
We're not allowed to do that, are we?
Yes, you are.
Without a ticket?
Yes, because I will be there,
And you're the operator.
and you can operate with me, just so long as an operator is there, you can operate. You can't operate on your own, but you could operate with me there. Else is a radio amateur, you can do that. So this will give you some experience, right? Problem with contests is you get very tired because they go way to the wee hours of the morning. So, you know, but you don't have to, if you want to stay, hey, we welcome it. But if you 4 o'clock in the morning is not your thing, then okay, we understand that, because it's not my thing. Okay, so I just want to mention that again, and I'll send that all to you. Okay, I guess we're ready to go. So, without further ado, Bob Heath, VA3BZ, I'm his reflection, which is VA3ZB, and people mix this up all the time. Bob has had a very lengthy and industrious career in radio communications. It's quite a long list as to what he has done. It's just marvelous. And he worked on the Dew Line. He worked for Ministry of Vines and Forest, I think they called it in those days. And he taught for many years at Sioux College physics and electronics. So
Don't forget math.
and math. So he's pretty high up there in terms of knowledge. He's been an amateur for a long time. And he has one
Want
of
the
the
travel
best
card that
radios
actually
you can
helps
buy.
you travel?
Costs them
Welcome to the
$4,000.
world of yes.
The K
Paris last minute?
Telegraph K.
Yes.
So he knows his business. He's going to talk to you
a little
about
over 3, actually.
a little over 3. So this is a transmission line. So go ahead, Bob. I'll get out of your way.
Oh, you want some? Oh, well, that's easily done. There you are. So you already know who I am, and that's me right there. It happens I'm also that there, which is the US call. And I hope everybody has recovered from yesterday. Too much turkey, too much dressing, too much mashed potatoes, etc., etc. What a way to go, huh? All right, and tonight's topic is transmission lines. And these notes I've handed out, I was under the impression, I wrote those back in February. I was under the impression that those were available on the club website. I don't know whether they are or not. I was also under the impression that they were on the disc that you were given, but I had a fast scan over that last night and discovered they weren't. So I printed copies out for everybody, and what I have to say is pretty well in those notes. In fact, my very best lecture would be to simply stand up here and read those notes to you. But I think you'd find that very boring. So what I have to say, I will certainly miss some of what's in my own notes, and I will certainly say a few things that are not in those notes. So if you pay attention to what I have to say and go home and read the notes, it should pretty well cover all the bases and maybe some extra as well. I have a couple of drawings on the board behind me, but that's for reference later on. Just to begin with a note of caution, on the Industry Canada database, if I remember correctly, there are 971 questions all told. And the test that you write will have 100 selected from that, more or less at random. Not entirely at random, because they're divided into groups. And what they apparently try to do is to get a representative number of questions from each group. So it's semi-random. And the questions are not divided up entirely evenly by topic either. There tends to be a greater emphasis on their own work, Industries Canada's own work, in other words, the regulations, which is all just as well, because Industry Canada answers to some of their own questions are either wrong or conditionally wrong. Where that happens with respect to transmission lines, I'll tell you about it somewhere along the way. Fortunately, these discrepancies are not all that widespread, so it shouldn't have any serious effect on whether you make the grade or not. And you've probably been told, but maybe not, that the way these multiple choice questions are answered, 100 of them, is only the right answers are counted. You've probably heard of marking multiple choice questions, sometimes done by taking the number of correct answers and subtracting from that the number of wrong answers, and that's your score. Well, if you get 50 of them right and 50 of them wrong, what do you get? You don't get anything. Well, that's not the way these are marked. It's simply a matter of how many are right, and that's it. So it's always worth your while to make a guess. Well, that's not the way you don't know, because after all, you've got 1 chance in 4. There are 4 options to every question. So you've always got 1 chance in 4 of getting the right answer, even if you don't understand the question. So always take a guess. The wrongs are not subtracted from the rights. Okay. Transmission line, what we're referring to, of course, is the transmission line that is used to get your signal from your transceiver up to the antenna, and conversely to get the signal received on the antenna down into the transceiver. When I first got an amateur radio license, the transmitters and receivers were entirely separate. There was no such thing as a transceiver at the time, and most of us built our own transmitters, and those who had the time and the knowledge and the patience and everything else would even build their own receivers. I didn't, but I did build my own transmitter, which was CW only, Morse code only, because it's much simpler, particularly as it was in those days, because the only modulation method, well, I shouldn't say the only, but the almost only modulation method of the time was AM, amplitude modulation, and this required a substantial increase in complexity and cost. I was one of those that didn't have the dollars available to handle that, and you needed a bit of extra power as well, because amplitude modulation is not a particularly efficient method of transmission. There's only a few hobbyists and guys that like to be different that are using it today. Single sideband is by far the most dominant method of amateur radio communication on the HF bands and on the VHF bands FM. But in all cases, we have to, by one means or another, get our energy from the transceiver up to the antenna. And this is what today's story is all about. Unlike moving water from one place to another, you can do it with almost anything you like. You can use copper pipe, plastic pipe, iron pipe. Doesn't matter whether it's straight or crooked or anything else, just so long as it'll get the water from here to there. Be a good idea not to use candy pipe. It would dissolve, wouldn't it? And other such problems as that. But we're very, very limited in what we can use for getting radio frequency energy from one place to another. And there's really only two common methods. One is to use open wire line, and this is an example of it. This is just two parallel wires separated by plastic in between. Actually, this stuff is made with the webbing complete, and they just use some kind of a wheel to chop parts of it out. After all, you don't need all of it. It's only there to keep the wires separated, and they could cut away quite a lot more than they do actually, but the plastic is cheap, so why go overboard? The other option is coaxial cable, and this is an example of a piece of coaxial cable. A particular cable, I think, is RG58, which is the military designation. This is just a piece with connectors on both ends that I sometimes use as a test cable. But with a piece of this long enough, or this long enough, you can go as far as you want. One thing that's critically important with any of these transmission lines is what's known as its impedance, or characteristic impedance. And the characteristic impedance of this, which we commonly call ladder line, is about 450 ohms. The characteristic impedance of the most common coaxial cable that we use is 50 ohms. What does it mean? Well, to explain in detail what it means technically is pretty involved, and I'm not going to do any such thing as that. But I think the easiest way to understand this is that if we have a transceiver that has a 50 ohm output, a 50 ohm connector for the transmission line, and if we have a transmission line, forget these two things. If we have a transmission line which has a characteristic impedance of 50 ohms, and if we have an antenna with a feed point impedance of 50 ohms, we have what's known as a perfectly matched condition, and under this condition, maximum power will be transferred from the transceiver to the antenna. Under any other condition, if all transceivers today have a 50 ohm output, but if either the transmission line or the antenna do not have characteristic impedances of 50 ohms, then you'll have an unmatched condition and you will get less than complete transfer of power. Well, power is fairly expensive to generate at radio frequencies, so you might just as well, make use of all of it and match things up properly. Unfortunately, there is no antenna that has an impedance of 50 ohms. The common dipole antenna, the most common antenna used in amateur radio, in free space has an impedance of 72 ohms, a characteristic feed point impedance of 72 ohms. And curiously, in many publications, etc., this is a number that's carved in stone. And the fact is that with real antennas that are operated over the real Earth, the feed point impedance is not 72 ohms, but something less, or in some cases more, depending upon the particular height over ground. And it's also influenced by any nearby metal objects, metal poles, metal buildings, or whatever. It is possible to measure what it is if you've got the right kind of test equipment, but very few people have. And they don't need to, actually. But what happens if you don't have a match? Well, I've already said you don't get a complete transfer of power. What happens up here is that the power that goes up, and it moves as a wave motion of voltages and currents along the transmission line. And if there's not a proper match here, some of that power is reflected. Remember, I said for the moment, forget these things are here. Some of the power is reflected and goes all the way back to the transceiver, which at the moment is operating in a transmit mode. And it has to be soaked up by the output stage of the transceiver. And these transceivers are not designed to soak up very much power. For instance, if all of the power were reflected, which would happen if there was a short circuit up here, all of the power would come back, and that would destroy the transceiver just like that. Nobody wants that to happen when you have to pay $1,000 or more for one of those things. So we want to avoid that. I remember I said that the RF power moves as a wave motion, and if power is reflected, it too is reflected as a wave motion. Now, it happens that waves of all kinds, electromagnetic waves, waves within transmission lines, sound waves, can run into each other, and they don't bounce off each other or anything of the sort. They just simply pass through each other. You can see this very, very easily by dropping 2 stones in a puddle. If you drop 1 stone in a puddle, you see waves move out in a circular fashion from that, and eventually they just become so small they disappear, and when they come to the edge of the puddle, of course, they're gone entirely. But if you drop 2 stones simultaneously, they don't have to be the same size, and watch what happens, and you'll see that the wave motion from each of those just simply passes through the other one unaffected. That sort of thing happens with all kinds of wave motions, including sound. When you have trouble understanding, supposing all of us start talking at once, please don't do that. But supposing all of us start talking at once, you'll probably not understand what anybody says. It's not because of any collision in the sound waves passing through the air. It's because of the fact that there's just a lot of different voices coming into your ear, and you just simply can't sort them out. This could be easily proved by using, say, 10 different audio oscillators operating at 10 different frequencies, and then filtering out each of them with a proper network at audio frequencies, and discover that the filtered sound from each source was an exact reproduction of what started out, was not affected in any way by the apparent collisions of the sound in the air in the room. The problem then is not collision of sound wave motion in the air when a whole bunch of people are yakking at the same time. It's the inability of your ear to be able to listen to 10 people simultaneously. You can listen to them, but you don't know what they're saying. I have even more trouble than that. As being very long in the tooth, I've become somewhat hard of hearing in recent years. And I've discovered something that I never knew before, that very often with hard of hearing, hearing distortion also occurs. So if any one of you says anything to me or asks a question, I may have to ask you 2 or 3 times to find out what it is you're saying. It's not because I can't hear you. I can hear you very well. It's just that my ear distorts what you have said, and it's especially difficult for me when, well, you know, some people mumble. Okay? What did he say? Well, these people don't open their mouth very much. Well, for me, those people are absolutely hopeless. Most people speak quite clearly, and I don't have any particular trouble. I didn't have any trouble with Bruce, for instance, when I was sitting over at the side there. I did have quite a bit of trouble with some comments made by some others of you. Good English. All right. So we've sorted out the matter of antenna impedance, and we've also sorted out the matter of the two only ways that energy can be transferred from a transmitter to an antenna. Actually, it is possible to feed an antenna. This is a very common term, and sometimes our transmission line is called a feeder because it feeds RF energy up into the antenna. It is possible to feed an antenna with a single wire. But when that's done, the feed wire itself radiates, and taking into account the fact that your feeder now starts right at the transmitter, means that energy is being radiated right from the edge of the transceiver outwards, and a lot of that energy is being radiated close into you, and except other than when very low powers are used, this often causes trouble with getting into especially microphone lines and causing distortion that way. To use a single wire feeder is not a good idea. You don't need to know anything about this actually, because all of the questions in the data bank deal with using 2-wire transmission lines, either coax or ladder line, or this is not the only kind of parallel wire line that's possible. This kind of thing has been at one time or another over the years available in impedances of 72 ohms, 150 ohms, 300 ohms, which was very, very common at one time with TV twin lead. This, which is nominally about 450, but is actually somewhat less. And the favorite of amateurs in years long gone by, back as far as, say, the 1930s, out and out open wire line, typically spaced by about 15 centimeters, and held separate by some kind of insulated spacing material. Today, if we were doing that, the obvious choice would be some kind of plastic. Plastics were not available at that time, so what was commonly used? Wood. But wood is a lousy insulator when it gets wet, especially some kinds of wood. So the typical way of doing that was to boil the wood in a pot of hot paraffin wax. And that was enough to make the wooden spacers waterproof, and this was the most common type of transmission line used before the Second World War. I've only seen one of those in Sault Ste. Marie since I've been here, which is a long time. And that belonged to VE3 DYR. He was using one at his motel, the Catalina Motel. Some of you may even remember have seen it. It has since come down. He doesn't have it up there anymore. What defines the impedance of a piece of? I said this is 450, typically or nominally 450. This is 50 ohms. Well, it ultimately is defined by electrical characteristics, but it actually, from our point of view, can be defined simply by the physical measurements. In the case of parallel wire line, it depends upon the ratio between the diameter of the conductor used and the spacing between the conductors. And if it's scaled up proportionally, in other words, if I double the diameter of the wire and I double the spacing between them, the impedance remains the same. In some broadcast transmitter applications where very, very high power is involved, parallel wire line has been used with spacing something like that, and the material for the conductor is actually a piece of pipe. A similar situation exists for coaxial cable. This is a cross section of what coaxial cable is like. It's just exactly what the name specifies. There is a center conductor. This is a cross section. There is a center conductor, typically copper, insulating material, and then an outer conductor. With almost all coaxial cable, the outer conductor is braid. It's braided material, that is, it's wire, small diameter wire that's braided together to form a cylindrical conductor, but made of braid. Again, the story is the same. The impedance of the cable is determined by the diameter, the ratio between the diameter of the inner diameter of the outer conductor and the outer diameter of the inner conductor. And again, if you scale it up proportionally, the impedance remains the same. So it's possible to make 50 ohm coaxial cable that's, well, I've seen some, I think it's as little as maybe a couple of millimeters in diameter. And the largest I've ever seen is about 6 inches in diameter. The coaxial cable used by the CBC transmitters in the CN Tower in Toronto, and both of those transmitters they have down there are 50 kilowatt, 50,000 watts. The energy is routed around between, you know, they have alternate transmitters, so they need ways to pipe this energy around to be able to switch it, and eventually, of course, it goes all the way up to the antenna stacks on top of the tower. But in the transmitter room, and I've actually been there to see it, it's approximately, I think actually nominally it's 6 inches. And of course, it's not braided wire they're using for the outer conductor. It's copper pipe. Copper pipe, 6 inches in diameter, and although I've never seen the inner conductor, I imagine it's a piece of copper pipe as well, possibly the size of your thumb or somewhere along that line. So in the case of both coaxial cable and parallel wire line, the impedance is determined by the ratio between the sizes of the two conductors. And that makes it possible to scale up or down by any amount you want. The impedance has absolutely nothing to do with the frequency or the length. There's absolutely no connection between frequency or length for the characteristic impedance of coaxial cable. There are a number of questions on the in the database that bring that particular matter up. There's a device called a Ballon. Ballon happens to stand, it's a contraction of the word balanced and unbalanced. You take part of the word balanced and part of the word unbalanced and put them together and you get Ballon. It's a device for being able to match balanced devices to unbalanced devices. Well, that's exactly what we've got here when we're using a typical dipole antenna with a coaxial cable. The dipole antenna is inherently a balanced device. It's got the same amount of wire on each side of the feed point. This is a balanced line, but coaxial is not. So it would seem as though if you want to use coaxial cable to excite your antenna or to feed it, same thing, you should use a Ballon to get from a balanced to an unbalanced, or to get from an unbalanced to a balanced condition. And these are available quite widely in ratios of 1 to 1, 2 to 1, 4 to 1, 6 to 1, and even I think 9 to 1. The only thing you really need to know about that is a matter of the relative impedances. Let us suppose that you have a dipole antenna that has a feed point impedance of 100 ohms. That happens to be possible, but it takes some real doing to accomplish it, but just suppose. And you're using 50 ohm coaxial cable to feed it. Well, the ratio between 100 ohms and 50 ohms is obviously 2 to 1. 100 divided by 50 is 2 to 1. So a 2 to 1 Ballon would be an appropriate choice for that, to both match impedances and to get from the balanced condition to the unbalanced condition. There are two other types of Ballon that are commonly used. One is known as a current Ballon, and the other is known as a choke Ballon. And the choke Ballon comes in various sorts. The Ballon I first spoke of is just known as a voltage Ballon. It's the only one Industry Canada considers within any of their questions, and the only thing they consider is a matter of matching impedance ratios. In my opinion, these things are not even necessary, and it would be better not used. However, since those are the ones that are in the database, you need to know about the resistance. And as I say, all of the questions deal with matching impedances. So you just simply take the impedances that are mentioned in the question, supposing it's 300 and 150. Well, 300 divided by 150 is 2 to 1. That's the Ballon you need, a 2 to 1 Ballon, and so it goes. A number of the questions within the database speak of grounding the sheath of a coaxial cable. It's not actually necessary to do that, although what the whole thing hinges on is what's meant by ground. Now, to most of you who are, I assume, relatively new to electronics, when you think of ground, you think of the stuff that you dig your garden in and so forth, real ground. Well, in the electronics business, the chassis, this thing here, on which circuits are built, the metal chassis, is also commonly referred to as ground, or sometimes circuit common. Now, to those in the business, whenever the term ground is seen in writing or people speaking, those within the business know automatically which kind of ground is being referred to, whether it's a real earth ground, whether it's a chassis ground, or whether it's just a circuit common, as occurs in the case of circuit boards. You know, a circuit board, there's really no chassis there. It's just a printed circuit board, but it always has a common. In some printed circuit boards that are both the top and bottom surfaces are used for printed circuit lines, I was wondering whether to say fairly common or what to say. In some cases, the one side is left untouched, and this is the circuit common. And any place from the top of the board where a common is needed, a ground, there's just a wire stuck through and soldered to the ground plane underneath. But that's only the case sometimes. But on a printed circuit board, there is always a circuit common somewhere, and this also is commonly referred to as a ground. So you really need to know what particular ground is being talked about when it's mentioned. And Industry Canada, in their questions, they simply don't distinguish between any of those. So you kind of need to scratch your head a little bit and decide what they're talking about. When they say, and they do, or imply in some questions, that a coaxial cable, that the braid, the outside conductor, needs to be connected to ground, what it really means is that it needs to be connected to the chassis of the device it's coming from. In other words, the transceiver. In some cases, the transceiver itself might actually be connected to real ground. Mine is by a piece of wire that goes out to a ground rod, but it's not actually necessary. And in fact, it's not even possible in satellites. Where are you going to find a ground for a satellite? Or it's virtually impractical if your station is up on the second or third floor of your house. An RF ground that long is almost useless. But again, it's not necessary. As far as the circuit working properly, The chassis ground is just fine. So I recall one question in the bank. It defines a coaxial cable as one in which the outer conductor is connected, the sheath is connected to ground. What ground? Well, if it's chassis ground, circuit common, yes. Certainly not earth ground. So just one of those things that you need to sort of keep an eye on. Another little problem comes up fairly frequently among the questions. It regards the burying of coaxial cable. Coaxial cable comes in not only a wide variety of types in terms of size and what the conductors are made of and so forth, but also in terms of the outer covering, which is some kind of plastic. In most cables, this outer covering is PVC, polyvinyl chloride. And polyvinyl chloride is neither weatherproof nor waterproof. However, as far as Industry Canada is concerned, all coaxial cables are waterproof, and you can do whatever you want with them at any time. So that's another point that you need to be aware of. When it comes to something like temporary operation, say for a field day operation, any coaxial cable that you can buy, the cheapest stuff available, which is the only thing you can get downtown, by the way, there's no problem. You can put that together on a field day site and run a piece of coaxial cable through a puddle, and it'll get you through the weekend okay. But for long-term use, if you want your coaxial cable to last, you need to get either weatherproof or waterproof coaxial cable, and that costs more money. But to Industry Canada, all coaxial cables are waterproof and weatherproof. Just keep that in mind when you run into any questions about them. There's another thing that comes up too with respect to the use of transmission lines, both coaxial cables and parallel wire line, and that's further routed. With coaxial cable, because of the fact that you've actually got a complete shield around the whole thing, you can put coaxial cables anywhere you want along metal surfaces. Very commonly for people that have towers, the feeder, the coaxial cable that goes up the tower, is laid right against one of the legs of the tower and even taped to it. No problem. Don't do that with ladder line or any other kind of parallel wire line. As a matter of fact, you can't even lay this against a metal surface of any kind. Industry Canada in their questions implies that the metal surface, a grounded metal surface, the metal surface does not have to be grounded. For instance, the siding, the aluminum siding on a house would not ordinarily be grounded. It might by accident, but certainly the people that put it on are not going to attempt to. And it's quite possible that the various sections of aluminum are not even connected to each other electrically. As far as siding goes, it doesn't matter. There's no need to do that, to bond them together. But it doesn't matter. The very fact that it is metallic is where the problem comes. If you were to take a piece of this and to, say, tape it up against aluminum siding, the performance would be degraded very, very seriously. Another example, for instance, is that with using coaxial cable, if you wanted to, and your antenna was directly over your house and it was convenient, you could, if you want, providing it was waterproof coaxial cable, run it along the bottom of an eaves trough, inside, and down the drain pipe, and bring it out at the bottom, and that just might happen to be the handy place to run it into your shack in the basement. Of course, whenever it rained, your coaxial cable sitting in the eaves trough there would be underwater, no problem, with good waterproof coaxial cable. But you'd be out of business trying to lay this stuff in the bottom of an eaves trough, even when it doesn't rain, because it would be against that metal surface. That's the primary disadvantage of open wire line, that you must keep it away from metal surfaces, grounded or not, and you also must keep it away from itself. When I started out here, I had this piece of coaxial cable all coiled up. If by chance you've got a little bit of extra feed line and you don't feel like cutting it off and refitting the connector, you can just coil it up like this and lay it on the floor or hang it up somewhere, and there will be no problem whatever. Do not do any such thing with ladder line. By coiling it up, or even allowing two sections of it to kind of lay against each other, that will definitely degrade the performance. There will be interaction between the two, and if you happen to have a perfect matching situation to begin with, you certainly will not have when you bring two sections together. No such the coaxial cable. I love this stuff. Why? Because it is very low loss. Very, very low loss. Much lower loss than any coaxial cable, and this means that you get more of your energy up into the antenna. The guy like VE3OTL who spoke to you last Thursday, he's got a real antenna farm. He must have upwards of 10 different antennas, and with a whole bunch of lines coming into his house from all over the place, to use ladder line would be almost impossible. But with coaxial cable, you can have leads coming in from a whole bunch of antennas, gather them all together in a big bunch, wrap some tape around them, and bring them all through one hole into the house. In my case, I'm a very simple guy. I've only got one antenna, and I only need one feed line. And it's a little more difficult to get a feed line through the wall than a coaxial cable, but not much. So parallel wire line, ladder line suits me just fine. 7:55. Time for maybe a little break?
Yes.
You think so?
Sure.
Let's go. I'm getting thirsty.